Hello, and today we'll be discussing our research on the design features of commercially available math games for 6th through 8th grade students. My name is Jillian Choquette, and I'll be presenting alongside Preston McCormick, and we are undergraduate students at Sam Houston State University, and our advisor is Dr. Emma P. Bullock. So the purpose of our research was to rank commercially available digital math games developed for students in the 6th through 8th grade for selection in a larger future study based on the framework for assessing the effectiveness of digital mathematics game-based learning. And now Preston will be covering the background of our research.
So today I'll be discussing what the research was based on as the theoretical framework. It was based on artifact-centric activity theory, or also known as ACAT. Children's activities are framed by how they interact with our technological tools they're using and with the design features in that specific tool. Ladle and Kortenkamp's artifact-centric activity theory, or ACAT, provides a useful lens for exploring how this interaction occurs. ACAT considers the relationship among the subject, a child, the artifact, a digital math game, and the object, which is mathematics. The rules are also included, which mean mathematics didacts and design principles, and the group, a child's peers and teacher. Figure 1 depicts this relationship. The focus of our inquiry and our future study occurs along the main axis of this picture: the subject, the artifact, the object, and the center line that connects all three, where the child is interacting with mathematics, the object, through the use of digital math games, the artifact, and in the upper right corner, the right triangle, which includes the rules and principles that help design this artifact according to the object, Ladle and Kortenkamp. A key question to ask in a relationship is, how do the design features in the digital game help the child interact with mathematics? It's a pretty good question. And using ACAT as a lens for our inquiry, we will focus on how the design features of the artifact, the digital math games, broker the internalization and externalization of the mathematics that children learn while playing the games.
So what is the effective digital educational mathematics games? So there's thousands of commercially available digital math games to students, especially in the grades 6 through 8. So generally, we wanted to focus on digital educational games, which are most effective when they include, based on El Castillo and Van Looy, the specific learning outcomes and motivational outcomes. So specific learning outcomes, we start with situational interest, SI. Situational interest is where the game stimulates interest in the content matter. Performance, where the game succeeds in achieving the learning goals, is defined by the game developer, and transfer, where the game stimulates application of the learned content to real-world situations. And then we have the general motivational outcome criteria, which will include enjoyment, where the game succeeds in creating an enjoyable game experience, and motivation, where the methods used in the game are more motivating than other instructional methods. So for our analysis, we created acronyms for each of these criteria: situational interest, SI, performance, key, transfer, T, enjoyment, E, and general motivation, GM. So for the effective digital math games continuing, in addition to the general criteria, we hypothesized that DMGs also need to have the following high quality design features: essential criteria, and then nice criteria that we would prefer to have in our games, but are not essential. So to begin, we have simultaneously linking, SL, which is types of design features act as linking mechanisms between different mathematical symbiotic systems. In other words, they facilitate a connection between one mathematical representation and another representation in the game in more or less abstract ways, either symbolically, visually, or audibly. So for an example, if we have an asteroid angle game, if we were to create an angle and make it larger, symbolically, the design of the game would also increase the angle. So as the student moves one element, another element also moves in the game. So continuing, we also have creative variation, CV, which are types of design features that are elements in the game that support the development of the student's own representations of the mathematics. So changing color or design or sizes of what they're working with in the game. And then we have the focus constraint, FC, types of design features focus and constrain students to mathematical information in the game that supports students' computation and abstraction. And then we have the focus, the correctness feedback, which is just a nice element, which are types of design features are representations that tell the user whether their actions within the game lead to correct mathematical solutions or not. So for example, a big X when they're incorrect or a green check when they're correct. So then we have the guiding feedback, which are types of design features that are representations that point the user towards a correct mathematical solution without directly telling them that they are correct or not. So for example, a little help button or a little guiding feedback that kind of just assists but does not exactly give the answer. So then we also have the efficient speed, types of design features that are representations that help the user more quickly interact with the digital math game, is if there's a time limit, or if they don't answer correctly, there's a decrease in the game score. And then finally, we have mathematical motivation, which are types of design features that are representations that encourage persistence during gameplay.
So what is our future goal? Well, we want to be able to conduct an experiment to test if the hypothesis holds for DMGs created for our 6th to 8th grade math games and our children. If there is a significant difference between DMGs, which are ranked high in the general categories, but low in the math specific categories. Furthermore, are there differences in children's learning between DMGs ranking high quality and all 4 essential categories versus games ranked high in only some of the math categories? So that's our goal. So our question: are there commercially available games for 6th to 8th grade children? There's thousands, but which fit these criteria that we could use in our future experiment? So now on to our methods. So our census research design. This type of research design is used when our research wants to list all elements in a group and measure one or more characteristics of these elements. So for our data collection, we search the Apple Store and the Google search engine using terms like educational math games, 6th, 7th, and 8th grade to compile a list of commercially available websites and apps. To date, we have found over 95 websites and apps with over 500 games. For instance, one website, one app could have 20 games. So this is how we get so many quickly. So today we have also played and ranked 261 games. And over 12 months with 10% of the games double coded to ensure inter-rater reliability, and exploring digital math games protocol. By using this, what we did before we started, 2 people, Jillian and I, we had to play the same game. And the reason why we did this is so we could grade on the same categories and get a consensus of how to grade these games. So for the data analysis, frequency counts. Excel spreadsheet filters summarize rankings across the games and assess which games fit the criteria for our future study. So if we're on to our results, Jillian will continue.
So this is a graph explaining the analysis of all our analyzed games. So for example, we had out of 261 games, we only had 30 games that were able to be a yes, completely creative variation. Where on the other hand, we only had 196 games out of 261 that had correctiveness feedback. So we really were able to look and compare each of the games where we only played 261, where we still have a lot more to play. And then, so what is this? This is the criteria needed for our future study. So our goal is to have 9 games, and 9 games, so we have 1 specifically in each grade and then 1 category. So for example, in grade 6, we need 1 game that is ranked high in all 7 math-specific categories and all general categories. We also need 1 game that is ranked high in 4 math-specific categories, SL, CV, FC, GF, and all general categories. But we also need 1 game that is our control group that is not ranked high in SL, CV, FC, or GF, but ranked high in all our general categories. So what does this mean? We had only 4 games out of 261 games that ranked high in all general categories. but none of these games ranked high in our essential specific criteria that we are looking for this research project. And I'll let Preston take it from here.
So for our implications, based on our preliminary results, we will continue to play the remaining games on our list because we have quite a few left. We anticipate playing over 500 games by the end of this data collection. If we're unable to find the appropriate games for our future study, we're going to need to either alter our future study design or maybe look at towards creating our own digital math games, which will fit our criteria. And so for today, these are the references we used in the slides and for our research in general. Thank you, Jillian. Was glad to be here. I've definitely been glad to be here and glad to work on this research project, and our advisor, Emma P. Bullock. Thank you.